I don't want to get bogged down in definitions because everyone has their own resilience definition, everyone has their own robustness definition. Just to say that for me, in this talk, we're talking about short-term, dealing with short-term environmental changes. And animals do that with lots of things. They can do this behaviorally, they can do it nutritionally, they can even go down and start reallocating resources between life functions. And Laurence will tell you all about allocation in her talk, and Fred as well, I think. But the key thing is, we think about these things, we need to look at the dynamic. We need to look at how things change through time. So we have that expectation that we will find resilience within a time series pattern, and then we start to make assumptions about that. And I like the idea of resilience as the elastic band. Something comes along and deforms the time series, stretches the animal, and then the animal responds, the challenge ends, and it comes back again. Oh, okay. So we're going to use this differential smoothing, and we're interested in the issues that go with it. And for one of the key issues is, when did that environmental perturbation start, and when did it end? And you can look at that in different ways. You can do experiments where you impose a challenge. This is an example, and then it's very easy. The challenge was between day 4 and day 6, and that is because I was in charge. I changed the feed of the goats. Here they had their normal ration. Here they were back on their normal ration. Here they only had straw. So you know exactly when it started and when it finished. And in this graph, each line is an individual goat, and I've just simply joined up the data. I haven't smoothed anything at all. But we can see that goats, when you put them on straw, they eat less. We knew that. What's interesting is how they started to deal with that, the consequences. So if we look at milk yield, we can see, not surprisingly, they eat less, they produce less milk, but they bounce back pretty quickly. But we start to see a little bit more variability. And the deeper you dig into the system, the more you will start to see emerging the different ways in which animals cope with the same challenge. So this is the example of milk protein content, and now we see completely different behaviors. And now we have to start to think about, how do we actually model this? How do we sort out the biological signal from the noise? And there are lots of different ways of doing that. One way is to make some fairly strong biological assumptions. Over here, we're on the normal feed. There's no challenge. So we would expect performance to be flat line. Here, something's happening. And to be honest, if I'm measuring milk yield, I only have 3 points. So that greatly limits the model I can fit. I can't fit a 5-degree polynomial because I have 3 points. So I can fit a linear slope. And then here, there's some kind of recovery. And in this example, I choose to fit a quadratic. This is what is shown up here. So that's splitting it into a pre-challenge, plateau, a linear, then a quadratic, and then they come back to some level. And if I do that, I can get for each individual animal coefficients, 1 for the plateau, 1 for the drop, and 2 to describe this coming back. That's a way of synthesizing my data, and then I can go on and I can, for example, cluster according to different shapes, and I can begin to see different types of response. But I'm making some very strong assumptions. For example, I'm saying that what happens here is a linear effect. And in this case, for some animals, well, nothing happens, or they go on after that point. But in order to get somewhere, you need to make some assumptions. And this is a model which can be useful. We've used it quite a bit. I have a postdoc who is called Marcello, and he has used this. He's written a document describing how to do this with the R code. He's made a video. So if this is something which interests you, then you can get in touch with Marcello, and he can provide you with the code and the tutorial and everything. But it is just one of many different ways of fitting these kinds of things. So I've pinched this slide from a colleague who made a kind of survey of all the different ways of doing things. Here's what we've just talked about, but you can see there are lots of different ways. This is actually the model which treats the cow as if it really were an elastic band. Take a model from physics and say it. And then here's some of the smoothing things that we'll come on to later. When you start to look at all of these, first of all, we come into this question that we talked about before, the trade-off between ease of use and biological interpretability. So the damped spring model really is saying we assume that cows are elastic bands, or goats are elastic bands, or fish, this was a fish paper actually, are elastic bands. You stretch the fish and you let it go again. Or we can just fit some splines, differential smoothing. And we can do an in-between, a statistical smoothing, but based on some fairly strong assumptions. So that's the first point. The second point will come out when we consider the different kinds of challenge that we can look at. So we can have planned challenges, like we've just seen with the goats. We know when the challenge started, we know when it ended. This is the same thing in the fish. There was a confinement challenge here between 20 and 60 minutes. So we know exactly when that period was. And you can see that the elastic band model fits quite well. But very often, we have time series data from precision livestock, and we don't actually know when the challenges happened. We need to find ways to detect when there were perturbations and to somehow quantify those. And we're interested in things like the amplitude of the response, the rates of the recovery. And this is the example that we're going to look at in a little more detail. So it's our friend differential smoothing. We've already briefly talked about functional data analysis. We'll look at it in a little bit more detail. It basically assumes that within your data, there are two populations of data. The population of data which comes from the distribution of what the animal is normally doing, and the population of data which comes from the distribution when the animal is in an altered state. Second equation in this talk. This is the equation for optimizing the functional data. So minimizing this. And if we break it down a little bit, here we have our series of measurements, which are modeled by some kind of smoothing, a set of what's called basis functions. And I've used spline functions, B-splines. And over here, we have a penalty function. So we want to minimize the difference between the predicted and the observed, between the smooth and the real. But we penalize that smoothing based on the curvature of that model. So here it says the curvature in the second derivative. And when we come back and play with the data afterwards, you'll be able to see that there are parameters in the R code which, for the lambda, for the base functions, and so on. And the two major controls over the fitting are that roughness penalty, and we'll see that in a second, and which data points you put in the first place. So you can apply a kind of filtering and decide to exclude some data points or downweight them. And that's actually useful. But let's first look at the roughness penalty. So here are the data smoothed with a very small value for the roughness penalty. So the fitted curve really follows the data. If I now increase that roughness penalty, you'll see what happens. So now we have a big roughness penalty, and now the data are very much ignoring all of the small wobbles. They're just taking out the general trend. So we can begin to see that if we smooth the same data set with two different roughness penalties, we can begin to see that we might be able to get the difference between this curve and this curve. So we can go a step further. We can, at least in part of the smoothing, decide that some of the data points are not of interest to us. So if we're trying to get at what the cow would have done if it wasn't perturbed, we could say, well, we're not interested in including data from all of the perturbations. So these points here, which have large negative residuals, we would exclude them, at least when we're trying to get the fit of the unperturbed animal. So this comes back to that assumption saying there are two populations of data. If we really want the unperturbed, well, these are not data points that are part of that cow's normal distribution for unperturbed. So we get rid of them. That will have the effect of pushing up the unperturbed curve. You can also do that by other ways. You can do that with things like quantile regression. And quantile regression, you use boundaries on the distribution of residuals, and you give different weights to those points in the regression. And typically what's happening here is we give much less weight to points that are below the 60% quantile. Those are details, but the idea is you can decide which points are in the population that you consider to be the normal population for that particular thing you're measuring. Put that together. So here we have the data smoothed with a small roughness penalty in blue, and in red the data smoothed with a much bigger roughness penalty and offset to ignore what's going on down here. So that pushes the curve slightly up. And in my world, as a biologist, I would say this represents more or less the phenotypic potential of those animals, and this is the response to perturbations. And I can start to calculate the difference between there and there, how long it lasts, and so on and so on. And that's where functional data analysis is very nice, because you very easily get the derivatives. So this is the rate of change of the blue curve. And every time it crosses 0, I can go and put a cross on here. And I can use that to start to calculate features. How are we doing for time? Oh, it's coffee time. Tough, I haven't finished. We will wait 5 minutes. You could do that lots of different ways. This is a dynamic linear model, which does nice filtering to take out. And that has been used to go a step further. So Guillaume Lenoir used that shape relative to an expectation about how his data should change, and then did genetic analysis on both the slopes and the variability around that slope. That's one way. Then you have these models which I call hard function models. What you do with a hard function model is you say, we know the underlying shape of the animal, what the animal would do if it was not perturbed. So I can fit that shape. I can fit a Woods curve. That's the blue line here. And I can do it in such a way that I move it up to really capture what I think is what the animal would have done if it was not perturbed. And that leaves me free to then calculate all of the perturbations relative to the hard function. That's quite complicated, because you assume a shape for this curve. You have to then do the nonlinear fitting. And then you may be thinking, well, why do that when we could just do the differential smoothing we did before? The problem with differential smoothing is that there's no hard reference to where that curve should be. It's simply based on the data. So if you have, like this, a perturbation which goes on a long time, then inevitably, at some point, your smoothing will kind of dip down into that space. So if you're interested in short-term perturbations, the differential smoothing is a good technique. If you want to get at the long perturbations, it's a problem, because it will effectively do this. Your baseline will eventually get dragged down into that perturbation. So you'll minimize, or even miss completely, something which is going on. However, the cost is that you assume that all cows have a lactation curve which fits a Wood function. And that can be useful, but in general, cows don't read the textbooks, so they don't always fit. So the data-driven functional data analysis is easy to apply. We don't assume anything about the functional form, but it will fail for long duration perturbations. If you take a hard function, PLM is the paper that I just quoted you, perturbed lactation model, it's harder to apply. There are strong assumptions about the functional form, but you can get at these long term. So again, the choices depend on the objectives. And there are actually ways where you kind of get the best out of both worlds if you can. So maybe we stop for coffee here and we'll finish off afterwards, and then you can play with some data. Yes, sorry, Master, go on.
So in the data for the goat challenge experiment that you were showing, I couldn't see the number, but I could see that there was a delay.
Yes.
From the time you stopped giving animals good food. Now, and I could see that there was also variation in the delay in the response between different animals. Did you find any sort of other things that could be associated with this delay to response? Can we draw any conclusion for the resilience of the animal based on this delay?
In that particular analysis, we ignored that. We simply said, we have a model here, we can capture some of the variability. We didn't explore that. And effectively, that model is not capable of estimating that delay without a modification to the model. So we didn't look at that, but it could be interesting to do so. And I think in some way that kind of has been done in what you've done, Marie. We'll see that on the last slide of the talk. So we come to two last points. And the first one starts with a very important question. Modelers are very proud of their models. And they will explain in great detail. Is this not true, Masoud? We will explain in great detail what we've done and how it's clever and what it does and how it's elegant. So a very important question to ask a modeler, always. So what? Or more carefully, do these perturbations that we're capturing actually have anything to do with real resilience? We've measured some features, they look nice, we have an experiment, but does it actually relate to reality? There is a huge need to be able to validate what you do. And I know this talk is not about that. But when you come to resilience, it does pose a question. And this is something Masoud said at the beginning as well. We don't have a direct measure of resilience. There's nothing you can measure which is resilience. We have things which we think may be to do with resilience, rates of response, rates of recovery, but we don't know. The only thing we can do is measure or try to validate against something which doesn't exist. So we need to go and find something else, perhaps the consequences of a good resilience. All other things being equal, if an animal is resilient, we may expect it to live longer. So maybe we want to validate against that. That's not easy, and the trick in the phrase was, all other things being equal. So we have a real challenge to validate. So there is a paper here which digs in a little bit into that issue of validation. How do we do? But what I'm going to do is to show you an example from a very nice piece of work by Marieke Popper. This was her part of her PhD. And she did something nice and pragmatic. So this graph we've seen before. This is from one of her papers. She got rid of the long-term time trend. Long-term time trend, yes. And she was interested in the remaining. And the pragmatic thing she did was to say, I'm not going to worry about rates of recovery or rates of response. I'm just going to calculate the variance around this. And I'm going to assume that animals which are less resilient have a bigger variance than animals which are resilient. So the more it wobbles around the baseline curve, that's my measure. And the neat thing they did was they had data from a very large number of cows in robotic milking farms in the Netherlands, nearly 2,600 farms. So she was able to fit her lactation curve to all the individual animals, calculate the residual variance, took the log because of the distribution, and then looked at how that was related to some genetic parameters. One thing that was interesting was that phenotypically there's a positive correlation between milk yield and log variance. So higher producing animals tend to have more variability. And what?
That's common, no? The coefficient variation will say that the higher the mean, the higher will be the variance.
Often we have scale issues, yes? But why would, biologically speaking, the variability increase just because the measure increases? For me, proportional errors, or proportional variance is linked to proportional errors.
Okay, you say that the variance will be the variance among any population, not within the error. Okay.
I think for milk yield, I wouldn't necessarily say that I would expect the measurement to be poorer or to be a proportional error. I'd expect it to be an absolute error. So I wouldn't expect it to scale with milk yield. But that's just my view. Because they had this large data set and they had the pedigrees of these animals, they were then able to look at the genetic correlations. And what you can see is, for example, there's a negative genetic correlation with longevity and also with a range of health issues and persistency and so on. So this is actually a way of saying we have this measure, this proxy for resilience or part of resilience, and we've actually been able to show that it correlates genetically with things that we would expect to be impacted by resilience. Longevity of the animal, frequency of disease, and so on. So for me, that's a good example of someone who's taken it all the way from trying to get up a proxy and ending up with a test. Yes?
Just to be sure that I understood the correlation. So the more variation there is, the less longevity will be,
Yes.
but also less issue with the health and ketosis there will be.
That's a good point. The results show that there is...
But isn't this in the direction that like higher breeding value is good and not like in the terms of that it's animals more susceptible?
That's the thing I don't remember in the paper, yes. Certainly the conclusion of the paper is that the more variation, the more disease. So maybe what you're saying is right.
I don't know.
That they have adjusted, that the...
From looking at the.
They've given a common sign.
I was just surprised by the longevity going in the same way because
Yes. The conclusions from the paper were that the correlations that you would expect between the proxy and all of the things like longevity and disease frequency suggested that this was a proxy for resilience. I must admit I don't remember exactly how the table is put together, but thanks for pointing that out. And there's a series of papers. I think this is the first one. There are 3 or 4 papers where they looked at different elements of that. And for me, it's a nice example of a good pragmatic approach to adding a brick into this resilience story. Sorry for the dodgy answer. Okay, this was just a break between subjects, but her work was done within this project Gentor, which is the sister project of SMARTA, doing resilience and efficiency in dairy cows. And there's lots of things in Gentor about resilience and efficiency which, okay, they're on cows, but I think they're relevant to other ruminants as well. The last point, briefly, is about combining measures. We talked about the fact that it was unlikely that the phenomenon that you want to look at, in our case resilience, is captured by any one single measure. So you probably want to think about fishing in different measures, and then the problem is how do you combine them? And this usually gets fairly hairy fairly quickly. So you need to go and find the people who can really understand and manipulate these models. I'll give you 2 examples. One is about degree of infection. So we'll come back to the mastitis that we talked about. And very quickly we'll talk about the pipeline which Marie has put together for doing multivariate analysis of milk measures. The idea with the mastitis thing was to say that we can't directly measure the impact of mastitis by one simple thing. We know that, for example, the conductivity will be affected if the blood-milk barrier is impacted. We have inflammation markers such as somatic cell score, other enzymes and so on. We wanted to combine those and see if we could get at a degree of infection. So this is the final equation of the talk. So here's a time series model. This is state space model. So you have whatever your y variable is. It could be the somatic cell count, it could be the conductivity, and so on. The k represents each of those variables. A long-term time trend, so getting rid of the overall long-term time trend, the short-term fluctuations, and then the noise. And the argument was that once you've got rid of the longer-term time trends, in all of these multiple measures, the short-term time trends should be correlated. They should all be reflecting the same underlying process. If that's true, then we can replace this by that underlying process, which is our degree of infection measure, and we weight each of the different components according to this lambda, this proportionality constant. So it's a reasonably simple way of combining, but it requires the assumption that those things are correlated and they're not overly lagged in time. Where it takes us is that we can calculate this degree of infection, and we could test it. So we have the degree of infection here, and we have days from a point at which the cows which had infections were treated. So they were treated by a vet at day 0. And we can see this degree of infection rising and then dropping off again. And that is relative to control animals who did not have a mastitis. And we were very pleased with this because we were looking for detection systems. And you can see here that the error bars differentiate already several days before the time of treatment. So this was just one example, this is published, of a way of combining measures. But it did require a certain amount of assumptions. It strengthens our indicators. We capture multiple facets of the infection. It's more complicated. That's not a good thing. For us, it was important as well because we could show this progression, this change. And so we can start talking about degree of infection. We were getting a bit fed up with detection systems that were based on sick versus healthy, black and white. There's a gray area. So for us, it much better reflected the biology of the system. And finally, I just wanted to show you this pipeline, which Marie has developed. So I showed you the goats and the milk composition. We've taken that a stage further with a bigger data set with 14 different milk metabolites. So you have, for any one metabolite, these kind of graphs where it's flat, then it rises, and with lots of variability. So the pipeline smooths those with natural cubic splines, adjusts them for some of the unwanted environmental effects, and then uses functional data analysis, but in the multivariate way. So functional principal components analysis. And if you have any questions, you can ask Marie, not me, because I don't understand it. But it allows you to get out a principal component for all of this, which in a sense is capturing both the multivariate and the time dimension. And then the idea was to go and then use that to identify different groups of goats. There was a design part which was we had animals from 2 longevity lines, but it turns out we couldn't really go very far with that. But we could do unsupervised clustering. And when we did that, ta-da, we get out 3, I say we, Marie gets 3 different clusters. And the interesting thing is when you look at the survivability of those 3 clusters, some of them were significantly different from others. So it seems as if there's something in the milk measures which allows us to identify animals which have different survival probability. So we're doing the same thing as I showed you before. We go all the way through to showing that this actually works to a degree. But it does get quite complicated because you're combining lots of different measures. And that's always an issue. If you need to combine the measures, you really need to have the statistical backup to do it. And I think that's more or less the end. So we come to the conclusions. It is a challenge to gain biological insight from time series data. You really need to think your questions carefully. Statistics on its own won't get you there. Masoud said the same thing, I agree. Clear goals is the key, because that allows you to make choices on the trade-off between ease of use and biological meaning, what you consider to be the biological signal relative to the noise, how you're then going to smooth, and how you're going to combine. Of course, the need to validate. And then just to come back, because this for me is, biologically speaking, the key. Whatever you measure is not a direct mirror of the thing you think you're looking at. It's only one reflection of the underlying biological phenomenon. And that for me is the reason where we need to do differential smoothing and then to combine afterwards. And that is that for the talk. Okay, so we have some 40 minutes, I think, until lunch. I don't remember what's in the program. Yes? Okay, so I did say I wouldn't talk about machine learning, but I did shove in one slide because I found a nice definition. But you can read that later. There's some bibliography. And the practical parts, we have a data set called 5 Goats, named after the famous burger chain, 5 Guys. It looks like this. You have the identity of the goat, you have the date, you have the days in milk, and PL is milk production. In French abbreviation is always the other way around, production laitière. that's the data set. What I suggest you do is that you have a look at the data, so you plot. See if you think you want to filter or not, and then play around with smoothing. In the code, there is code for doing it with functional data analysis. That's quite interesting. That allows you to adjust the roughness penalty, see how that changes things. And you can also do it just with a polynomial. I think there's a bit of code as well to show you how to do that. If you use the functional data analysis, you'll need this library. And so you can start to think if you can get as far as differential smoothing, but in 40 minutes that might be a bit tough, unless you're really good at R. And I haven't dealt with the offset. That's something that you can pick up otherwise. But ask yourself as you do this, what assumptions you're making, and are there any issues that you want to come back to at the end? So I think that was more or less. So you all have the data set and the R code. These are just examples of the plots that you can get out. Okay, nobody can see that. What you'll find at the top of the code is the basic parameters you need for the FDA. So you can play around with the roughness penalty, for example. What I've done is to create a loop, so extracting each goat one by one, and then plotting. And you can turn on or off the type of graph and decide whether it goes into a file, or you can, if you block out at the bottom in the plots, there is this X11 double bracket, which is remmed out. If you remove that, you'll get the plots directly on the screen. I'm a crap R coder because I don't do it very often. So, but Masood's going to help us if we have problems with the R. So, yeah, play with that.